Hello, good morning everyone. Today we will go through the last part of this course, which is the designs through the frequency response technique. So the goal of today's would be to again design the compensator for the control systems, but in particularly this week we will use the frequency response technique. As we have seen last week, we have gone through the bot plot, okay, which we plot the magnitude plot as well as the phase plot, okay, and from those plot itself we can figure out what is the gain margin as well as the phase margin. Okay, just a refresh, this is the phase margin when the magnitude of the gain is 0, and the gain margin is this difference when the phase is 180 degree, right? Okay, so move onwards. As we have seen previously as well, we are able to actually adjust the gain by doing certain things, right? So here when we adjust the gain itself, we actually adjusting the transient response, right? So here the transient response uh, the transient response through the gain adjustment, as you can see previously, if we are using the root locus, we should able to adjust by drawing the lines, and then we find the locations of the locus where it passed through that particular point, okay, or the lines, the damping ratio lines, as and so on, right? But in the similar way, okay, we would want to use this frequency response to actually adjust it, okay, but this time we would go through the frequency response by so-called using the phase margin as well as the damping ratio. Okay, so just recall the phase margin is closely related to the damping ratio of the system, which we can actually uh, form from this particular open loop functions of a unity feedback system. Okay, so given as such, this is a second order system, right? In this system itself, okay, when we try to relate this system with the phase margin and the damping ratio, we note that these functions, which being expressed as the functions of damping ratio as well as the natural frequency itself, okay, when we take into the account, this is the relations between the phase margin and the damping ratio, right? And as an approximation, if you would want to get a quick check, right, you can always approximate the phase margin as well, okay, divide by 100, okay, so you would able to somehow get the so-called damping ratio itself, okay, and this approximation would be good, okay, when the phase margin is less than 70 degree, right? As we can see from the previous lecture as well, okay, we can actually design for the compensator, okay, the compensator or the gain adjustment itself, okay, by drawing the bot plot, okay, then we find out based on the relationship between the phase margin and the damping ratio, okay, then we would be able to figure out what would be the suitable frequency, okay, to give us the desired phase margin, and then from there we would able to adjust the gain accordingly, right? So we just go through these examples before we move to the real compensator, which we have learned previously related to the PI and PD, okay, but in this lecture we will focus more on the lag compensator as well as the lead compensator, and at that particular sections, okay, when it's come to relate about the steady state error, okay, then we will touch on that, okay, events, right? So the from these examples, um, we have seen this is a positions control system, okay, which we use a motor on load, right? Then we have a power amplifier, right? And we have this so-called preamplifier, which we can adjust our gain, right? So we try to find the value of the gain itself, okay, that would allow us to get a 9.5% overshoot in the transient response, okay, when a step input is being applied. So here the steps would be very similar, right? So you just have to go through it several times, okay? So this is a guide, so-called a guide for you to get the desired value of k, right? So if you later on get more familiar, then you can easily skip several steps to get what you want, right? So just follow this step by step, right? So first we would choose the k value equals to 3.6, okay, which you have learned previously, okay. When we try to set at the 0 dB, okay, at the low frequency, okay, so remember we have set the so-called 1 decade before the break frequency, we call it as a low frequency, okay. So we set that as k equals to 3.6, right? So once we get that particular k, okay, which you learned previously in the previous lessons, okay, then from this so-called uncompensated conditions, okay, or non-adjusted conditions, what we would do now is we would try to check what would be the damping ratio which corresponding to this 9.5 overshoots, okay. So you can actually get this uh, relationships, okay, in chapter 4, right? And from that you should able to get approximately damping ratio equals to 0.6 itself, okay. Then from this 0.6 is is actually related to 59.2 if you are referring to the previous equations, okay, the equations that we have gone through just few minutes ago, right? So you get these equations, and if you still recall, this is very close, right? Where you have the phase margin divided by 100 should be equals to your damping ratio. You can see that the approximation is very close, okay, when the angle is less than 70 degree, right? So in that case you can see that they are very close to 60 degree, right? Okay, so meaning to say your calculation is now correct, okay, somehow, yeah, it's correct, okay. So based on that, what you need to do now, we get 59.2, okay. In the phase plot itself we will just calculate, okay. 59.2 is actually equals to negative 120.8, okay. 180 minus 59.2, okay, because this is the solution, so called, okay. That's where the root locus will lies on our, yeah, in the line itself, right? So based on that, okay, we try to shift this, okay. This is the margin, okay, that we want to shift, right, from the phase plot itself, okay. So we will try to shift it to 120.8 degree, okay, and that occurs when the frequency is about 14.8, okay. So now at this frequency, the gain is found to be, if you draw this line up all the way, okay, the gain is actually found at approximately 44.2 dB, all right. So since you know how to use mathematical tools like MATLAB or Scilab, you can actually plot this out, okay, and draw it, okay, or get all this information from there. All right. So in this frequency itself, okay, you get minus 44.2 dB, and this means this magnitude has to be raised, okay, to 0, okay, to yield the required phase margin, right? So this is the things, or the gap or the margin that you have to raise, right, due to the shifting of this phase margin itself. Okay, so from that 44.2, how we can further calculate is that we know that we always use 20 log our magnitude. Okay, so that magnitude, which is 162.2, okay, will give us 44.2 dB. Alright, so we have this 44.2 dB as our target, and we want to know what is the magnitude that we have to adjust. Okay, so you just have to recalculate. Okay, since this is log, you can always turn the equations into a exponential form. Okay, so in that way you can get the 162.2, right? So this is the magnitude that you have to adjust, right? So from that magnitude 162.2, you have to multiply by your initial gain, okay, that we have set initially, okay, when this line is 0, right? So which is 3.6. When you multiply them, then you get 583.9. All right, so that would be the gain that you should adjust, okay, in order for you to get the so-called desired overshoot, right? So if we double check again, that would give us roughly 9.48 percent overshoot, right? So this would be the gain adjusted open loop transfer functions after you have performed. So remember, this form is this one, okay? You just multiply, right? So you should able to get this. Okay, so these questions, or this form, is very similar to your test one. Okay, the last question C, I guess, okay, where you have a GC and your functions, right? So you just have to simplify them, then you will get something like this, right? So this is how you should able to uh, obtain the desired so-called transfer functions or equivalent transfer functions for you to evaluate their performance accordingly. All right, so if you are intended to find the static constants, okay, then you can use the final wall value theorem, okay, to in order to get this kv, right? But if you notice from this so-called performance that we get, right, we have this kv equals to 16.22. Okay, how to get this one? You just k, you get k, right? The z0 is 0, okay, then you have 36, 100, okay, you just multiply that by the pool. All right, so when you divide, you should get roughly this number, right? So you get the kv values, all right, meaning to say, in actual, after you adjust this gain itself, you still have a so-called a steady state error in between them. All right, so now come to this steady state error characteristic, where how we can actually uh, check or estimate the steady state error from the frequency response. All right, in order for us to observe this steady state error in the form of a static error constant, which is the kp, kv, ka, right, you have to use the unnormalized and unscaled but log magnitude plot, right? Meaning to say, you should draw the original dot plot instead of the asymptotic type of plot plot, right? You don't need to normalize them, okay, in order to get this exact so-called value. All right. So if you plot it using the unscaled, unnormalized form, then it will not start from zero anymore. It will start with a certain value, right? Okay. So based on that, right? So this positions constant, or the KP itself, is related to the type 0 system. Okay, and we know that this type 0 system itself, okay, the initial values would be equals to this value, okay, which is this m, right? The 20 log m, okay, equals to this, and this value is your m value, right? So meaning to say, for this type 0 itself, the kp would be your very beginning value, all right, very beginning value, okay, which is the, we would say, the same value of the low frequency axis. Okay, so at the low frequency, the intersections, so-called intersections with this y-axis, this would be your value of kp. So this magnitude would be your kp, okay, when you plot it according to the real magnitude, okay, not the normalized one, right? So this is how you would be able to get or estimate your kp position constant. Okay, so remember, unnormalized and unscaled dot plot, you have to use this. Okay, then for the velocity constant, then again you have this so-called gain, right, or transfer functions, right? And again, when we plot it out, okay, so the same functions now, okay, but then because of this, right, you would see that the uh, initial slope will origin from this particular point, okay, and this particular point itself, okay, when you extend it, right, so you, if you are looking for kp, it will be the starting point, right? So when you are looking for the velocity constant, which is the kv, right, then you would see this slope itself, okay, which is the negative 20 dB per decades. Okay, when you extend it to this so-called x-axis, okay, then it would be actually equals to this magnitude, right, this kv value. Okay, so therefore we would say that the velocity constant would be the same as the frequency axis. This is a frequency axis intercept. All right, so remember, you have to draw a minus 20 dB per decade and extend it, right, for you to get this kv. Then for the acceleration constant, which is considered the, when we consider a type 2 system, okay, type 2 systems, then again you have the omega square, and when we have this, it is related to minus 40 dB, okay, and you can see that when it is minus 40 dB, then you have to draw a minus 40 dB line, right? So you just draw a minus 40 dB line, right? So when you get it, then this value would represent a square root of ka, okay, sorry, ka, right? So this would be this value, but you have to put a square root because of this particular square terms there, right? So this is how you can estimate or obtain the static constant, okay, based on the dot plot, okay, the magnitude dot plot, right? So now come back to this compensator part, right? As you have seen previously, we say that we can improve the steady state error using a PI or a lag compensator. Okay, whereas when we try to control the transient response, we would prefer a lead or the PD type of compensator, right? So in this topics today, we will focus more on the lead and the lag. Alright, so we will not discuss about the PI and PD in these lessons. Okay, So we will try to formulate the compensator in the form of lead and lag transfer functions. Okay, so here the P is just to adjust the gain, right, so that you meet a certain specifications, but then it's not always what you would desire. Remember, when you shift the K value, sometimes it's out of the root locker, so you have to do the another adjustment, okay, which is the integral and the differential derivative terms, okay, to compensate the system, okay, and this is where this compensator comes in, right? So first of all, we will go through the lag compensations or compensator itself, right? So as you can see, when we try to compensate, then the system will become will shift or change characteristics, okay. Just a recall on the characteristics, such that for an uncompensated system, it would be unstable uh, when the magnitude itself is more than 0 dB, okay, when the gain is at 180, right? So first things first, you want to also ensure that the system is stable, okay, when we size or maybe design for this compensator, right? So keep in mind 180-degree positive value in the magnitude, it means unstable, right? So this is how you can see that if we use the original, the lighter blue one, okay, the the system will only become stable after this value, which is more than 180 degrees. So originally, meaning to say it may not be stable originally, okay. So the functions of this lag compensator now, it seems to have maybe two purpose, okay, either to improve the static error constant, okay, which is the original intent, all right, by lowering the low frequency gain. Remember, the KP is related to the low frequency gain, right? So if we can lower it, or somehow, remember the KV and KA also related to the starting point of the low frequency values. Therefore, we can actually improve the static error constant by adjusting the low frequency gain itself, okay, without later on causing instability, because when we lower it, yeah, lower the line, okay, means we increase the stability, right? Another one would be to increase the phase margin of the system to the desired transient response, right? So it have to come in pair when we design using this frequency response technique, okay, because of this characteristics, okay, 180-degree and 0 dB, right? So just an idea, okay, the lag compensator would reduce the high frequency gain through this so-called adjustment of the phase margin, okay. So you can see that originally, if it is 180-degree, okay, then the system is actually unstable, okay. And if you want to get the KV, okay, you draw a minus 20 dB per decades line, okay, you get the KV value, right? So in order to adjust this, right, so what we can do is we have to so-called reshape it through the 0 dB to the desired phase margin, okay, so that when we adjust it, okay, so you can see that this is uncompensated, and after we do a compensations, okay, this line will actually drop, okay, to a lower line, okay. So this is what the idea behind how it would change, okay, or the shape change, okay, when we adjust through the adjustment of the phase margin, okay, the phase value, as well as it is being reflected on the magnitude plot later on, okay. And also the red line itself is representing the lag compensator's phase margin as well as the magnitude, right? So as we know, the total systems, okay, for when we draw the butt plot, okay, we can total them up, okay. So when you have a lag compensator or additional of a component of the butt plot itself, you can do a minus and plus, okay, to your diagram itself, okay. So you can see that the lag compensator, if we put 0 at the beginning, so it doesn't change, okay, but then we after that we would want to reduce this value, okay, to a negative value, so that this line will now decrease, okay, so that it shift the kV value forward, right? Then by doing that also, we are adjusting the phase plot, okay, by shifting. You can see that originally we don't do anything, then at this particular point, okay, when we have this line going downwards, the phase margin also correspondingly shift down, okay, throughout this period, right, from 0, okay, then back to 0, right? So this is how we can you can see how this lag compensator do, right? So the characteristic of the lag compensator is it has a component of this minus slope, okay, before it retain or maintain to the original one, right? So this is the line, okay, and the corresponding phase plot would be due to this slope itself, the phase will change, okay, again downwards before it turns back upwards, right? Okay, so that would be how it would looks like, okay, for a lag compensator. So this design procedure, you can read it on your own later on, okay, if you are interested, okay. We will go through the examples directly from there, okay. It is much easier to visualize, okay, those steps, right? In order for us to do the design, okay, using the butt plot, we will need this so-called transfer functions of the lag compensator, okay. We will rely on this lag compensator, okay, where we have this attenuations factors, okay, these alpha terms over here, okay, which is a factors of this 1 over t value. All right, so recall this, okay, this would be the lag compensators terms that we will use when we design for this compensator, the lag compensator, using a frequency response technique. So this transfer function would be very similar to the root locus technique, okay. Don't worry, you can see in somehow some way it is related, okay, but only the terms now, we instead of a we use 1 over t, is very similar, right? So in doing the setting, we will rely on the initial gain, okay, the initial gain to meet the steady state requirement, okay, by adjusting the starting value, okay, and then later on, by after we adjusting the starting value, then the lag compensator minus 20 dB per decade slope will be used to meet the desired transient response, right? So that it would somehow cross the magnitude plot's frequency axis, okay, to get the 0 dB. All right, so this would be the transfer functions for a lag compensator, okay, and these equations would relate these attenuations factors respect to the phase margin, Okay, so you have this equation sine phase margin, okay, equals to 1 minus alpha divided by 1 plus alpha. Alright, so this is the relations between them. Okay, then after you get these attenuations factors, then you would able to find this Kc. Okay, this Kc value, the gain of your compensator would be the K value of your original divided by the attenuations factors. Okay, so you just keep this in check, right, so that you use it later on. Again, this is descriptions on how you may observe the dot plot accordingly, so you can again refer this later on when you are familiar with it, right? So that's would be the case for slide for you to go through on your own, okay, after you are clear with it. Okay, so now we quickly go through the examples, okay, how we would able to use the dot plot diagram to design for a lag compensator. In this case, what we would want is a 10-fold or 10 times improvement of a steady state error, okay, over the previously gain compensated system without or much changes to our original overshoots, okay, which is 9.4. Okay, remember previously we already get, or we already designed for the K value, okay, which meet this 9.5 percent overshoot, right? We get the K value around 500 plus, right? Okay, same problem. Okay, we extend from that particular problem now. All right, and from the previous value, we already get the KV value, which is 16.22. Okay, if you recall back, okay, it's 16.22. You can always refer back to the previous slides, okay, in the system. Okay, so in order for us to get a 10 times improvement now, okay, meaning to say this KV value have to be multiplied by 10. Okay, the constant must be 10 times greater. Okay, when this value 10 times greater, meaning to say the error will reduce 10 times. Okay, so we have to multiply by 10. Okay, so you get the KV equals to 162.2. okay, so now the value of the K would be again 10 times, okay, which is 5839, okay, 5839, okay, 10 times, okay, so that we get this so-called 10 times improvement. Okay, but then remember, as we increase the gain, okay, in order to reduce the steady state error, the locations of the root locus actually shift. Okay, therefore this come into the picture on why we should adjust or compensate it with a lag compensator. Alright, so now we would use 5839, okay, when we multiply by 100 again into our previous transfer functions, okay, 100 over here, okay, then we get 583900, alright, divided by the so-called values. Okay, so recall this. Right, now come to the adjustment. Okay, in order for us to get the lag compensator. Okay, so first of all, again, we would want to check, okay, in previous examples, the K value that we use, okay, which meet the damping ratio of 0.6. Okay, we get the line of 59.2. okay, 59.2, right? Now if we increase this value of phase margin by 10, okay, let's say we want to adjust it to by 10, right, in order to compensate the phase angle contribution to the compensator. Okay, this value 10 degree you can assume, right? So let's take it to be 10. So if we take it to be 10, then therefore it would become 69.2, and from that 180 minus 69.2 2 you get minus 110.8. Right, so you draw a line. Alright, so this happens to be, just look at the black line, okay, which is the uncompensated system. Okay, before we add the compensator. Okay, so when it intersect with the black line, okay, that occurs to be about 9.8 radian per second. Okay, so this is the frequency of it. Okay, so when we draw a line up, okay, to the uncompensated systems, okay, the black line, then we would see that that would be a 24 dB over here, right? So you will see that a 24 dB that we would get, right, at 9.8 radian per second frequency. Alright, so this is, remember, non-asymptotic, meaning to say this line is plotted using the real value, okay, not the normalized and so on, right? So based on this value 29 dB, now we have to so-called attenuate, okay, suppress this 24 dB to become 0, right? Because when we try to adjust this phase margin or phase margin, right, by adding the 10 degree, okay, into our design, what happens is that it causes this to increase. Okay, so in order for us to design for the lag compensator, we have to provide suppressions, okay, a minus 24 dB to the 9.8 radian per second. Okay, so how we can suppress this one, 24 dB. Alright, so we draw the compensator first. Okay, draw a line. Okay, so now what we can do, okay, how we can do it is that first we draw a minus 24. Okay, this is what we would want to suppress. Okay, instead of the bottom, okay, we start counting from 0 to minus 24. Okay, we draw a minus 24 line, okay, and cross it to the 0.98. Okay, so how we get this 0.98? Previously we are talking about 9.8 radian per second. Okay, what we would want is that we would set the higher break frequency, which is about a decade below the so-called break frequency that we would want. Okay, so that's why we would now select like a 0.98, where, okay, 1 decades before that, right? So at that particular line, so we cross it. Okay, we found this point. Okay, so at this particular point now, what you need to do is to draw a minus 20 dB per decades line, right? So remember how to draw. You just put a line from 0 to minus 20 per decade. Okay, then you shift this line, okay, so that you have a parallel line to it. Okay, draw until it crosses 0. Okay, from this particular point, okay, draw with this slope, okay, until it crosses a 0 line here. Okay, a 0 dB is reached. Okay, then from there you would notice that it's actually, for this case, it crossed this 0.062. okay, and now at this we will call this 0.062 as the lower frequency. Okay, lower frequency, right? So how we can use all this information to form the lag compensators parameters is that when it comes to here, we will form this 0 line again. Okay, remember we have previously the 0, okay, come down, minus 20, then straight, right? So this would be the components of our lag compensator, right? So now how we would want to put into this transfer function is that we have this kc, okay, kc value, right? Then we have 1 over t, okay, 1 over t value, 1, and then 1 over alpha t, right? So these three values we could actually get from all this value that we get, okay. What are those value is that this 0.98 referring to this value, okay, the 1 decades below, okay, this value, right? And then the lower one, okay, 0.062 would be this value, okay. So meaning to say we have 1 over t equals to 0.98, and 1 over t multiplied by 1 over alpha, okay, give us 0.062, okay. So if we comes to this, alright, so eventually we can recalculate, okay, to in order for us to get the 1 over alpha, which is 0.063, and this 0.063 would be this value, okay. So this is our so-called attenuation factors, okay, 0.063, right? How many times it would actually reduce, okay, or to in order for us to regain back this so-called unity gain, okay. So you will see that this is over 0.98 over 0.062, okay, when we have this so-called unity gain later on, right? So that is how you can fill up those value, okay, the kc, the 1 over t, and the 1 over alpha t, okay, from the plot diagram, right? So in that sense you would able to form this particular transfer functions, okay, where this terms comes from the lag compensator, right? And then the other terms would be come from your original transfer functions, right? So you multiply them up, you will able to get this, okay. So after you get this, again you would want to make sure, just make sure, okay, for when we come to design we always want to recheck, okay, whether it's correct or not, okay. You have to do an iteration, so you just adjust it again, okay. If it is far away from what you desire, okay, so you get this, okay, you just recheck again whether the actual value is proper or not. So eventually you get the kV values is 161.5, okay, instead of 162.2, which is very close. So if you can accept that one, then that would be good, right? Meaning to say it's already near to 10 times, okay, of your previously 16.2 yeah, 16.2 original, okay. We would want to increase 10 times, so eventually when we apply this transfer functions we get 161.5, okay, which is almost 10 times, right, where the phase margins also remain almost similar, right. So this is how you can see that the criteria after you do the compensations, the performance is close to what we would want to, okay. So this is how, by using the frequency response technique, we are able to achieve the desired steady state error specifications, right. Next would be the lead compensations. For the lead compensations, our intention is to adjust the transient response, which would be corresponding to maybe the peak time, okay, or maybe settling time or whatever it is, right, which again related to the the damping ratio and other parameters. Alright, so the lead compensator will increase what we call as bandwidth, okay, by increasing the gain crossover. Alright, and also raise the phase diagram at the higher frequency. Okay, so these are the two things that you would see later on when we use these lead compensations. Okay, how these lead compensators will do is actually a reverse of the lag compensator. Okay, previously in the lag compensator you have 0 dB, then is minus 20, right? So in this lead compensator is in the opposite direction, okay, which is the plus. Okay, so that the uncompensated one, okay, it will now adjusted to a higher magnitude. Okay, then also for the phase diagram, okay, or phase plot itself, it is again being adjusted, okay, uh, in the opposite directions, ups, okay, before going down again due to this line, right? So every time there is this point changes, okay, you have one line. All right, so due to this point changes, you have another line, right, going down. Okay, so the corresponding compensator, and what occurs due to this lead compensator is that the phase plot is now raised for a higher frequency. So from this particular point, okay, this point is actually being so-called raised up, right, because of this, okay, being raised up, okay, and because of the raising up, this point A, which is the intersect with the 0 dB line, is now shift to point C, okay, which is at the higher frequency. Okay, and because of that higher frequency, in actual, then the so-called phase margin also change, okay, to a larger bandwidth, okay, larger band, right? So that is the idea behind like the lead compensator. Okay, so again, the lead compensator transfer functions will be given by this, all right, which is again very similar, very close to the lag compensator. Okay, only terms that we use now is the beta instead of alpha, right? And now here also, instead of the pure alpha, we use 1 over beta, okay, the inverse of it, right? So that would be the case for this lead network or lead compensator transfer functions. All right, so keep in mind that this would be how it would looks like, okay, how it would looks like, the beta and so on, okay, for beta lower than 1, right? So you can see the changes in terms of the phase and the magnitude, okay, when the beta change. Okay, now again, you would need this so-called analytical expressions, yeah, analytical expressions, in order for you to design for the lead compensator. Okay, in the lead compensator, what you need is to figure out what is the maximum value of phase and what is the corresponding frequency when this maximum values of phase actually occurs, right? So in order to get that one, okay, based on this compensator transfer functions, again we have this relationship, okay, which is the phase angle of the lead compensator given by this relationship. And in order for us to get the maximum value, we would want to differentiate in respect to the omega, alright, and set it to 0. Then we would able to get the so-called maximum frequency. Okay, so we can eventually get the maximum frequency equals to 1 over t square root of beta, right? So this would be useful later on. Okay, and then the maximum phase shift, okay, of the compensator would be the maximum values, okay, would be given by this, okay, sine, okay, arc sine of 1 minus beta divided by 1 plus beta, okay. This again very similar to the previous lag compensator, the alpha, right? So you will see that the similarity in terms of the derivations or equations, because of the structures of the transfer function, is very similar, right? Only the way they are doing it, right? Then for the magnitude when it occurs would be given by 1 over square root of beta, right? So again, this design procedure you can read it later on, right, when you need, okay. We will just go through the procedure directly to the examples, alright. So here we have these examples given, again exactly the same problem, okay. A positions system, a positioning system, where now you want to design a lead compensator that give us a 20% overshoot, right? Instead of the previously 9.5% overshoot, now we would want to adjust it to 20% overshoot, okay. Yeah, we would just want to adjust it, okay, for so-called to to meet the desired design specifications, right? At same time, the kV would be equals to 40, all right, with a peak time of 0.1 second, okay. This would be the transient limitations, okay, in this problem, right? So if we would want to do from that, meaning to say we reset back to the k value, okay, the original one, right, without the lag compensations, alright. So come back to that, alright. We would start with the closed loop bandwidth, okay. We will want to check what is the closed loop bandwidth that we would require, okay, in order to meet the desired speed, okay. The peak time equals to 0.1, okay. This peak time equals to 0.1. This would give us the bandwidth, alright. So how to get this, okay, so you see this relationship, okay, in the previous lessons, okay, which is related to the bandwidth, okay, omega bandwidth, okay. You will notice that there is a TP, okay. That's why it comes to a point where, if depending on the characteristic that you want, if whether it's TP or TS, okay, or whatever it is, then you have to refer back to the previous lessons, okay, how we would relate that with the frequency of the bandwidth, okay, and we would try to get the bandwidth required, right? So based on the TP equals to 0.1, we just substitute 0.1, okay, and the damping ratio, which is we would say 20% overshoot, okay, 20% overshoot, we apply this, we will get about 0.456, okay, damping ratio. We would obtain this bandwidth frequency at 46.6 radian per second, right? So you can just try to put in your values later on, right, on your own. Make sure you try it, alright, so that you get familiar with putting in, okay, whether when you put the percent, okay, whether you should put 20 or 0.2, okay, that I left it to you to figure out, right? For example, this one, percent overshoot, what value you should put, 0.2 or 20, alright. So you have to try it so that you will know, okay, what value you will get, okay, in order to get this 0.456, right? So you try to put in all those value in, okay, and then once you get this bandwidth frequency, right, now in order for us to meet this specifications of kV equals to 40, then what we need is we have to adjust it again, right, based on the kV value, okay. We have this k, this is our desired kV, so meaning to say we have already get 40 over here, right? So okay, so this value is 40, okay, that we already know from this, right? Then in order to get this one, it referring to this value, okay, meaning to say this is unknown. Alright, so what we need to do is, based on the transfer function that we have, right, you fill in the 0 is 0, 0, nothing there. Alright, the pole is 36, okay, 100, and so on. Okay, fill it in. Alright, though then eventually you have 40 equals to k, a certain number. So recalculate, you will get the k equals to 1440. Right, again, try it, right, so that you would know what value to put in for z1, z2, p1, p2, and so on. Right, so once you get this 1440, okay, so again we put it back into our equations, multiply by 100 divided by s plus 36 plus multiply by again s plus 100, you get this transfer function to start with. Okay, so you would plot the plot diagram or board plot, okay, for it, okay, accordingly. Right, so once you plot it out, now you would want to start to observe, okay, to get all the parameters you would want to put into the compensators transfer functions, okay, the GC. Right, so first of all, again, 20% overshoots would give us 48.1 degree. Okay, so you can always refer back how you get this 48.1, okay, using the equations given previously, okay, related to the to the equations of the damping ratio, okay, OS. Right, so just refer to the slide number 7. Okay, then the uncompensated systems would now, as we have figured out previously, is 1440, and it has a phase margin of 34. Okay, so you just draw a line, okay, 180 and 34. Okay, so which is about 1 minus 136, I guess. Okay, so 34 degree of it, right? And when we cut through, you will notice that this black color line, again, the uncompensated one, when we cut through it, it is about occurs at the frequency about 29.6 radian per second. Right, so just draw a straight line to our magnitude plot. Right, so what happened is that again, assuming 10 degree of correcting factors, okay, for our lead compensator, and also we would want to increase, okay, so that we obtain this so-called 48.1 degree, okay, to corresponding to the 20% overshoot. What we would do now is we do a calculation, 48.1 degree minus the 34, okay, 34, okay, which we obtain due to the phase margin itself, okay, then plus our assumptions of 10% adjustment plus minus, right, so we would give a 10 degree, right. So if you go back to the design procedure later on, you would see a range of value that you can do an assumption from, I think, 5 degree to 15 degree, right. So you can select a value from there. Okay, so you start from there. Okay, so what you get now is 24.1 degree with a bandwidth of 46.6. Okay, so now again from the same line, what you need to do now is that you obtain this 24.1, and we would now want to use the equations to obtain all those important informations. Okay, we have to set the phase, maximum phase is equals to 24.1, and using that equations, okay, in presented earlier, right, you would be able to estimate the beta equals to 0.42, right? Once you get the 0.42, again estimate for the value, okay, of this GC when the so-called maximum frequency occurs, right? the Okay, so we get 1 over square root beta, which is we estimate as 0.42. You get this value, right? So this value uh, is corresponding to 3.76. Okay, it's corresponding to 3.76. Okay, so you can try, you should get 3.76 dB. Okay, so and because of that 3.76 dB, which cross to the is caused by this so-called lead compensator. What you need to do is now you have to compensate it again. Okay, when we compensate it again means we have to adjust or shift it. Okay, and this adjustment would be to suppress, okay, minus from positive 3.76 to minus 3.6, so that it would be adjust, right? So for that, again, use the same methods. Okay, we draw a line of minus 3.76, okay, cross it. Okay, so that particular point would occur at 39 radian per second. Okay, this would be what we call as a new phase margin frequency. Okay, so you have a new value of 39 there, right? So again, from this beta value as well, okay, you can calculate or estimate the maximum frequency that it occurs. Okay, so when you calculate this, okay, in order to get the 1 over t, right, so you have 1 over t unknown. Okay, this one you already able to get this one. Okay, and this omega maximum, okay, you have the omega maximum 39, okay, which you obtain from the dot plot, right? So put it in, you should get the 1 over t, and that 1 over t now you would get as 25.3, and because this is 125.3, then our 1 over beta t would be 60.2 based on the equations, right? This one, okay, when you multiply it, you get 60.2, right? So eventually you have obtained all the parameters that you need to describe the transfer functions for your lead compensator, which is 1 over beta s plus 1 over t divided by s plus 1 over beta t, right? So this is the values, right? So you just put it in, then you get the transfer functions, okay, for your lead compensator. Okay, so once you get the lead compensator, you just multiply them, right? Because we are assuming a cascade open loop of compensations, right? So you just have to multiply them all together to simplify into a single transfer functions, which is given by this, right? So again, once you have obtained this one, what you need to do is just to resimulate, okay, redraw this the dot plot, okay, to check whether the characteristics or the behavior meets, well, your desired specification or not, right? So this would be the actual lead compensator value, okay. And from this also we notice that the open loop magnitude response is about -7, okay, at -7, okay, at the frequency about 68.8, okay. So meaning to say, in other words, it means that the bandwidth actually exceed the requirement of 46.6, right? So this is 68.8, okay, which is higher, right, than the required 46.6 radian per second. Therefore, we would or we may foresee that when this bandwidth exceed the requirement, the peak time should be able to meet, right? but nevertheless you can always do the simulations, okay, and you'll notice that the kV maintained 40, right? No change. The percent overshoots almost maintained, okay, 22.6, okay, and the peak time is 0.075, okay, which is less than 0.1. So yeah, it's good enough to meet the criteria, right? So this is how you can adjust or obtain those value from the bot plot in order for you to form the transfer functions for your compensator, right? For the lag-lead compensations, we will not go through in details again. The idea is very similar. You just have to first do for the lag, and then next do for the lead, right? So you can always do in this way, okay. After you get familiar with this, okay, eventually you gain an idea of how you can adjust it simultaneously together, right? So once you able to gain that skill, then you can actually design simultaneously together, right? Where to look for all those phase margin and so on, okay, simultaneously, right? So this is how it would looks like, all right. But then since the alpha, beta, and so on may be confusing somehow, okay, so it's up to you what value you would want to use later on, okay. Then also they may want to replace the alpha with the gamma and so on, okay, to find so-called a ratio between them and whatever it is, right? So this is the idea on how you can design according to the problem or specifications, right? So here is the procedure. If you want to go through it, you feel free to do so, right? So we will not cover on that in detail, and same thing for this last part, okay, just an exposures to you. Actually you have gone through the root locus, okay. The root locus is good for us to plot the closed loop pool, okay, as a functions of open loop gain, and where we can see clearly how the root locus actually change, okay, where it should intersect, okay, to get the solutions. Then on the butt plot itself, it give more on the frequency, right? So you will see that the how the frequency will affect the performance, okay. So that would be much more greater when the system is have a higher order, right, greater than 2 and so on, right? So you can see the frequency change, okay, accordingly. But then somehow in the butt plot diagram, okay, where we have this gain margin and phase margins indications, the problem is that they may somehow ambiguous, okay. Ambiguous means looks like true, not true, okay. They have maybe two meanings, okay, because of the signage itself, okay. So they have a contradict stabilities information sometimes, right? So in that case we may want to apply this Nyquist criteria, right? So this is just an exposures the terms for you, right? We will not go through in this Nyquist, right? So the Nyquist will have a Nyquist plot, right, and it maps the Nyquist plot from contour one, okay, through your so-called transfer functions, okay, to another one. So you can see that the shift of the Nyquist plot actually shift to a part where again you can see that the stable part, right, instead of the unstable part. So you can form in this so-called mapping, right, through the Nyquist criteria, okay, which we may not cover now, right? So I hope that will give you an idea of when somehow in the future you may read certain controls related material, and if it happens to come to this terms called Nyquist, then you have the idea where it comes from, and the purpose of it is for you to design, all right, for the compensator, right? So I hope that would be sufficient for you to gain the basic fundamentals of control uh, throughout this course, okay, from the beginning of modeling, simplifications, then we talk about the steady state error, the stability, and then the two techniques, okay, which is the root locus and the frequency response technique in order for you to design the compensator or adjustment through the P or PI, PD, lag or lead, right? So that would complete the whole process of modeling to design of a compensator to meet a certain characteristic, right? So I hope that you enjoy this course, okay, and that would be the end of this course, right? So before I forget, so don't for make sure you go to the SMP to do the evaluations of the course, okay, through the PK07 form, okay, in your SMP. Then also you are feel free to give feedback through the Google Classroom, okay, or WhatsApp or whatever it is, okay, to highlight what is the good, the bad, or whatever it is related to these courses, okay. And a final reminder, there would be a final exam, okay, uh, which would fall on the 3rd of February, okay, 9 to 12, right? So the guideline of the final exams have been posted in the Google Classroom as well as in the WhatsApp group, right? So feel free to recheck that, okay, what is required and so on, okay. So remember, these evaluations of the course and feedbacks is related to the whole course itself, not only this chapter, right? And then any tutorial for this chapter, yeah, I will post the tutorial questions, maybe one or two questions, okay, tomorrow, okay, so that you may go through it, and we will have the tutorial not tomorrow, okay, it will be next week, right? So I guess next week is maybe study week, right? I'm not sure, right? So we will go through that as the final part of the lessons, okay. So any questions before we end these sessions? Any tutorials for this chapter? Okay, the tutorial will be posted later, alright? Yeah, next week will be the study week, okay. I'm not sure how many courses will have the final exam in your class, okay. So if you have an idea, just give me some hint, alright, so that I roughly know, okay. Beside this course, how many more? I think third year subject maybe three maybe, right? The rest you should like having the replacement and so on. Boleh dapat jawapan untuk test 2 sebelum ini. I will post the so-called answer scheme lah, right? Not exact answer, okay, because you can see the the parameter is based on your matrix number, right? So I just put in like the guide, okay, how I would give the marks for those without replacement test. 5 paper in total for us to sit. Oh, meaning to say you have 5 paper with final exam, right, Evans? 5 paper means most of you would have the final exam. Okay, that's great. Okay, okay, all right. So for those who repeat this course, I guess you have the experience of the final exam questions. You can feel free to check back, okay, what is the questions previously, right? For final exam, the questions will be similar with our test 1 and 2. Uh, yeah, sort of similar. Can you give extra notes or example question for chapter 6b and 7? Alright, I will try to cover that, okay, in the tutorial. Right, I try to cover as much as possible. Okay, but then yeah, you can always check back the textbook again. Okay, I believe the textbook have a good examples there, right? Any more questions? Okay, so if no more questions, then we will meet again next Friday. Okay, next Friday. So I will post the tutorial questions first, and then we will have the tutorial sessions next week. About assignment, can you give some idea how to do it? Okay. For the assignments, it's actually a so-called a bit open-ended. Okay, meaning to say whatever information is not given there, you can always assume, right? For example, the input, okay, whether it's step input, RAM input, or whatever it is, you have to do some assumptions, okay, based on the specification given. Okay, then from that, once you so-called frame up your problem, okay, whatever given there is not fixed, right? What is fixed is only maybe the equations of the printer, motors, and so on, right? But what are not fixed is the maybe input, the environment, or if you want, you can add disturbance or whatever criteria that make the problem more interesting, right? So for that assignments, what you need is you just refer back to the root locus technique. All right, since I've specifically mentioned that you would try to use the PID control, right? Therefore, meaning to say there would be a steady state error as well as a performance or the transient response performance that you may want to adjust, right? So based on these two criteria, okay, meaning to say when you frame up your questions or problem which is not uh, being defined very clearly, is that you have to tell what is your target steady state error, okay, whether you want to reduce it until zero for a RAM input or whatever it is, or and at the same time what is the performance that you would want to achieve. Okay, that particular problem may give you some ideas, okay, but then if you think that it is not sufficient, you can further improve it, right? So it's just a demonstrations of what you have learned and how you would apply all what that you have learned. Okay, so you may want to write in the form of report, okay, with introductions, where the introductions will specify with the problem that I have given to you, and on top of that, the setup, okay, meaning the other parameters unknown, okay, that you would want to include, okay, the performance criteria, the steady state error, and other things, okay, that you want to adjust, okay, and from that, then only you will start to design for your PID, okay. As you recall, okay, we don't touch on the PID design, right? But then the PID designs actually it's just the combinations of PI and PD, right? So you can do the PI first, then using that PI transfer functions, you use it for or adjust it using a PD, okay? So then you get the PID, right? Very straightforward, right? Or if you are keen enough, then you can also learn through the examples in the textbook, okay, given by Norman Lees, right? So there is a PID uh, procedure that you may follow, okay, maybe skip one or two steps in between them, okay, because some informations may be related, all right. So that's why you when you read, you may start to confuse why this and that, okay. You may just start with PI, and then from PI to PD, okay, you still solve the same problem. Eventually you will still get a PID transfer functions, okay, which have two part, right. And then I don't actually limit you to what you call the pure or the ideal PID. You can use the lag lead compensator to act as a PID control, right? So it's up to your creativity. So therefore I don't expect all the group have the same answer, right? Because of the setup and other things, the considerations that you may take care may be different from different group, right? So if you are satisfied with the design, then you do discussions, right? So basically your assignments, you have the problem, which is the introductions. Then from that you would frame up your design steps, okay, meaning to say just all your calculations related, maybe you start with the root lockers and so on, okay. Just present it in a flow, right. This thing first, second thing this, and so on. At the end, what you get, okay. So once you get that one, always do a simulations, meaning to say to check the final whether it actually meet the design specification or not, right. So do a simulation, plot the graph, right. Then from there you do discussions whether your design have meet the intended specification or not, right. So I hope that would answer your request. Okay, so first just start with writing, all right. Any more questions? Okay, so if you still have questions later on, feel free to WhatsApp, all right, or put in the Google Classroom, right. So okay, so that's all from me, okay, and goodbye everyone, bye bye.